So in our next example, we are going to look at horizontal compressions, and we are starting by looking at our same function of f of x again, and what we are investigating this time is what happens when we are graphing f of 2x. So let's think about that. If we have our point, I'm going to look at this point here at x equals 3 months, then what does it mean to now have 2x? So we want the function value here at x equals 3, but we want the function value already from twice the months further down the road. So we're wanting it at 6. So we want the function value at 6, which is 11. That's the point over here. But we want that already at 3 months. So we want that point over here. So it's basically we are speeding up the process. But when we are speeding up the process, that means we accomplish everything in less time, right? So that point kind of came half closer to our y-axis. And so in the same way, if I, for instance, look at my x of 1.5, then I would want the value from 3. 1.5 times 2 is 3. So we want that function value there, and so that's 13. So that's now here. And so in the same way we do it with all the other function values. So about here we then have 4.5, and everything basically gets squished together, gets compressed together, and so everything gets closer together. And the only point I want to point out, and the only point that doesn't change is the one where x equals 0, because 2 times 0 is still 0. So there the point remains the same, but everything becomes closer to that. So let's check how that works again with our points. So we again take all our data points and write them out. And then we are going to divide the value for x by 2, because we have found that, right, everything gets closer, comes closer to the y-axis, and because we are graphing everything, I'm using decimals, and so our first point becomes negative 7.5, 4, so the y value remains the same. So let me fill in the other ones, and I invite you to do that yourself as well. And so to summarize everything, we can say that our function gets compressed by a factor of 2, and since everything happens at double the speed, it takes half the time. So that's why it's the opposite. Or we can come back to the idea of, since the 2 is inside the parentheses, the 2x gets rebellious and does the opposite of what it appears to be doing, and basically you have to divide all the x by 2. Now we're doing an example the other way around, and as you can already imagine, is that will now be a horizontal stretch, and we are investigating our function at 1/12 times x. So this time around we again start with our table, because we now have already again an idea of that everything is happening the other way around. We can say that our x values will get multiplied by 12. Even though it says 1/12 times x, it will be 12 times x. So we're again starting by writing out our different points, and then we take all our x values and simply multiply them by 12. Therefore our first value becomes negative 184 for the y value, and so that's quite a bit bigger, but as you can see on our graph, we have a scale that reflects accurately what our points will be. So I'm first going to fill in all my points, and then I'm going to graph it. And now we can take our points and go ahead and graph them. And so we get negative 184, and then all the other points. And as you can see, with 108, we had to estimate that halfway between 90 and 120 is 105, and so right after that would be 108, and we'll do the same with 36. So we end up with this graph that is much more elongated, much more stretched out than our original graph, in fact by a factor of 12. So if you imagine that, let's say you would, instead of going 12 miles an hour, you would only go 1 mile an hour, or let's make it a little bit more realistic, instead of 24 miles an hour, right? Let's say you go through a neighborhood at 24 miles an hour, and instead you're going 2 miles an hour through that same neighborhood. You would definitely need 12 times as long in order to get to your destination. So our function gets stretched by a factor of 12, and again, since everything happens at 1/12 of the speed, it takes 12 times as long. So to summarize, we want to one more time look at our factors, how they can be either create a compression or a stretch. So we can say that if we have our function f of b times x, then and b is greater than 1, like in our 2, then the graph of the original function compresses horizontally by a factor of 1 over b. On the other hand, if the factor b is less than 1 but greater than 0, then the original function stretches horizontally by a factor of 1 over b. And I just realized I made one small mistake in the beginning when I should have actually said that our function that got compressed actually by a factor of 1/2. So I'm going to change that now to that our function gets compressed by a factor of 1/2. And it is correct that it gets stretched by a factor of 12, even though it says here 1 over b, because when we write 1 over b, now our b in that case was 1 over 12, so that ends up being 12. That second part, that was correct. And again, keep in mind here is that our b for the stretching part is between 0 and 1.